be another little like breather day where we're going to review trig functions. So everything you need to know for this course about trig functions, hopefully we'll cover today. Okay, so it's just the basics, and the purpose of the review is so that our next class, well, next class is our check-in day, but the class after that, we're going to talk about how to take the derivative of trig functions. So we need to sort of have them fresh in our mind and how they work. So then Monday is your project check-in day, so you should have as much of project 2 completed as you can before Monday so that you can compare with your classmates and ask me questions and get the most that you can out of that day. Okay, so today we review trig functions so that we can find and use derivative formulas for the next class. Okay, so remember there's 2 ways to measure an angle, 2 units. We have degrees and radians. And the way to convert between degrees and radians is to use the identity that 180 degrees is how many radians? Pi. 180 degrees is pi radians. So whenever you're in calculus class, you should always assume that you're operating in radian mode. We always use radians in calculus class, unless otherwise noted. Sometimes they'll give you a problem in degrees, but mostly if doesn't say anything else, assume radian mode. There's a very good reason for it, which will become clear when we do the derivatives of trig functions. All right, so if we have a function of the form a times the sine of b times x minus c plus d, or a times the cosine of b times x minus c plus d, we can tell some things about this function just by using the values of a, b, c, and d. Does this sound familiar? All right, what's the amplitude of these 2 functions? The absolute value of a, yeah, because a can be a negative number, right? But the amplitude is just the absolute value. What's the horizontal shift? C, yeah. And the period? It's related to b. It's not b itself. No. 2 pi over b. And the midline of the function, also known as the vertical shift, d. So the midline, it's at the line y equals d is the midline. Okay, so let's do an example where we take a real life scenario and we model it with one of these sinusoidal functions. So you've got a rabbit population that varies sinusoidally between 3,000 and 5,000 rabbits. So the last 2 times the population reached 5,000 rabbits was in 1990 and again in 2000. So we want to make a model for the rabbits as a function of t, the number of years since 2000. So I like to draw it first. Just draw it and then try to write an equation that will match the graph. So this is years since 2000. So negative 10 is 1990. 2000 is 0. 10 would be 2010. So I'm just putting these to remind us what these numbers are. Okay. Okay, so so it varies between 3,000 and 5,000 rabbits. So I'm going to put a 5,000 on the y-axis and a 3,000. Halfway between those two would be 4,000. And it was at 5,000 rabbits in 1990 and again in 2000. So I could change the color for the actual graph. 5,000 in 1990, 5,000 in 2010. I think I might want to change the scale. It's a little small. Put 10 here. Okay, so 1990, that's 2000, it was 5,000, and in 1990 it was 5,000. And this, because this is sinusoidal, it's going to hit a peak at the same at the same interval, right? So it would be 5,000 again in 2010. Make sense? Okay, and then it's going to hit its minimum value halfway between its maximums. So it will hit 3,000, its minimum, in 1995 and in 2005. And then the midline, the like halfway point between its max and its min, I like to draw in with a dashed line. And halfway between a max and a min, it hits its midline. So it'll hit the midline about here, and here, and here, and here. And then we can try to connect them with a nice smooth sinusoidal curve. And then we got to try to write a formula for it. Okay, so my general formula for a sinusoidal function looks like f of t equals a times either the sine or the cosine of b times x minus c plus d. And then we just fill in, we have to pick sine or cosine, and we have to fill in a, b, c, and d, and we'll have a model. Okay, so first thing I like to do is pick sine or cosine. So which of these do you like, sine or cosine, for this particular model? Sine. Why? Cosine. Why? Yeah, a cosine starts at its max, right? A sine starts at the midline. So you have to have a mental picture of what the regular plain old cos x and sine x look like. So that's sine, right? And this one, the bell curve one, that's cosine. Well, just because it kind of looks like a bell. I just made it up. One that starts at its max. Okay, so if it starts at a max or a min, it's easier to use cosine because then you don't have to shift. You can always use either one because they're the exact same shape, just shifted a little bit. But it's easier if you can leave out the horizontal shift. So I think I'm going to use cosine because my graph starts at its max, and so does cosine. All right, so I'm going to do cosine. Okay, my amplitude, that's the distance from the midline to a max or the midline to a min. So what's my amplitude here? 1,000. And then the period, how long does it take for one cycle to complete here? 10 years. 10 years to get from a maximum to a maximum or a minimum to a minimum. Okay, so to complete one complete cosine curve, 10 years. So that is my period, which is related to the value of b, right? Remember that the period is 2 pi over b. And I now know the period is 10. And so I can solve for b, right? And it turns out b is 2 pi over 10. So I'm going to put that in for b. Sure, yeah, I guess you should. Pi over 5, same thing. Pi over 5 times x. And then minus c, I don't have any shifting because cosine starts at its max, and so does my graph, so there's no shift. Just leave the c out. And then plus d, and d is just the location of your midline, which is where? 4,000. The amplitude is the distance from the midline to a maximum, or the midline to a minimum. No, it's half of that. Yeah. You use the period to find B. Yeah. Yep. And if you were given the formula, you could use B to find the period. Yeah. Yes.
Now, if you're trying to find the midline,
yeah.
it's not like pretty looking like that, you know what I mean? Is there a way you just find the max and min and then divide it by 2?
Average them, add them together, and divide by 2. Yeah. Yeah. So 5,000 plus 3,000 is 8,000. Divided by 2 is 4,000. So you can always find the midline by taking the average of the max and the min. Yep. All right. What do you think? Is this semi-familiar? Good.
So if it was like, if you did it with the sine, it would be x.
Okay, yeah. So if I had used sine, sine would start, sine starts on the midline, right? So that means I shifted right 5, right, for sine, because instead of being here, it's at positive 5. Oh, sorry, actually, that's at 2.5, right? So if let's write it out with sine. That's a good. So my amplitude would still be 1,000. If I use sine, the period's still pi over 5. The only thing that changes is my horizontal shift. Okay. So I just have to figure out what my shift was. So standard cosine would be on the x-axis. I mean, on the y-axis. The midline would start on the y-axis, right here. But instead, it is shifted to the right by 2.5. So remember, with transformations, how do you shift to the right? Subtract, yeah. So I'm going to do minus 2.5. So I could use sine or cosine. I just have to put a shift in with the sine. And if you're unsure, right, if these two functions are the same, and I was just discussing this with someone in the project. If you are trying to tell if your simplified version is the same as the thing you started with, a good way to check is to look at the graph of each of them, right, and see if they match. So I could do that here. These two functions are supposed to be exactly the same. So if I graph them both, they should have the same graphs. So let's do that with GeoGebra. Okay, so my first function was f of x equals 1,000 times the cosine of x, pi over 5 times x plus 4,000. Okay, so I got to change my scale. I got to be able to see 4,000. There we go. Okay, so there's f. And then my other one is also f. Call it g so that GeoGebra doesn't get confused. Was 1,000 times the sine of pi over 5 times x minus 2.5 plus 4,000. Oh, looks like I made a mistake. They're not the same. The shift, did I go the wrong way with the shift? Yeah, maybe. Let's see what happens if I make plus 2.5. Now they're the same. Okay, so I messed up. It's x minus the shift, and the shift was 2.5, so. Oh, I know why. I know why. No, so it's not the minus. Sine always starts at its midline and goes up. So let's look at my picture of sine. It starts at its midline and goes up. The point I was just looking at, this one here that I assumed it had shifted to, that's at its midline, but then it goes down, right? So I actually should have been looking to shift to here, right? Because that's at its midline and then goes up. So that is normally here, and it shifted left 2.5. So that's why it was plus 2.5. Yeah. So see, it's a good way to catch your mistakes. So in the cost function of the drum project, this is a great way to do it, right? Because one thing I asked you to do was like substitute in a value, an expression for h, and then simplify. If you're unsure if you simplified correctly, graph the unsimplified version, graph your simplified version, make sure they look the same. And if they don't, you know you made a mistake. Okay, so given these functions, what year and month will the rabbit population next be 4,500? So I'm going to do it two ways, algebraically and graphically. So the question is when, right? What year and month? So I'm going to be solving for x, or t. Sorry, these should all be t's. So I'm solving for t, and f of t represents population, so I need to solve the equation 4,500 equals 1,000 times the cosine pi over 5 x plus 4,000. All right, so I'll start by doing it algebraically. What do I want to do? What's my goal? Yeah, I want to solve for x. Yeah, so the first thing I want to do is isolate the cosine, right? I would like to get this guy by itself. Okay, so first thing I do is I'm going to subtract 4,000. So I get 500 equals 1,000 times the cosine of pi over 5x. We should use t, sorry. It's force of habit. Then divide both sides by 1,000 to get the cosine by itself. So I have 1/2 is equal to the cosine of an angle, right? And it's just some fancy pi over 5x is what I'm naming this angle. Okay, so I have to think about where on the unit circle does the cosine have a value of 1/2. So if you don't have the unit circle memorized in your head, get working on that. Okay. It'll be useful. So the first quadrant, if you remember, this is √3/2, 1/2. And then the 45-degree angle is √2/2, √2/2. And then the 60-degree angle is 1/2, √3/2. The quadrantal angles are pretty easy because they're just zeros and ones. And once you have that much memorized, the whole rest of the circle can be filled in using symmetry, right? So you're just going to memorize 3 points, basically. So which coordinate represents cosine? X. The x coordinate is cosine. So I have right here, that angle has a cosine of 1/2 because the x coordinate is 1/2. All right, where else on the unit circle will the x coordinate be positive 1/2? Yeah, down in the fourth quadrant, right here. Right. That point would have coordinates 1/2 negative √3/2. Right? Anywhere else? Nope, that's it. So those two angles, we've got 60 degrees or pi over 3, because we're working in radians here. We've got pi's in there already, so we should keep in radians. Pi over 3, and then what about this guy? This one. What angle is that in radians? This one? Yes. You could measure it as a negative, yeah. But the question is asking about, will the population be next 4,500? And so the angles in our example here are times. So I don't really want to use negative angles. Yeah. So here's how I count. So you don't have to like have them memorized. You can count and figure out what angle it is, just like you can count with degrees. So this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, which is just pi, right? 7 pi over 6, 8 pi over 6, 9 pi over 6, reduces to 3 pi over 2, and then 10 pi over 6, which reduces to 5 pi over 3. Okay, so I found two angles, pi over 3 and 5 pi over 3. And I asked for just the next year and month, but I'm going to give the next two just to be fancy. So that means that pi over 5x, that's the angle I'm taking the cosine of. That angle has to either be pi over 3 or 5 pi over 3. Okay. Those are the next two times where my angle will have a cosine of 1/2. And then I solve each of these for x. That's okay. Go ahead. Yeah. Yeah, but I used the unit circle to figure it out. The problem with using the arc cosine or the inverse cosine button is that it will only give you one of these, right? It'll only give you, for inverse cosine, it'll only give you the angle in the top half of the unit circle, and you'll have to figure out the other one. Yeah. Okay, so if I try to solve these, this says the pi's cancel, so I have x over 5 equals 1/3. Multiply both sides by 5, and I get x is 5/3. And here, x over 5 equals 5/3. Multiply both sides by 5, and I get x is 25/3. Yeah. So I had the cosine of some stuff. Anything you're taking the cosine of has to be an angle, right? So I have the cosine of some angle, even though it's written fancily, right? Cosine of some angle is 1/2. So I figured out what angles have a cosine of 1/2, pi over 3 and 5 pi over 3. So I said this angle, which is named pi over 5x, pi over 3, it has to equal pi over 3 or 5 pi over 3 in order for the cosine of it to be 1/2. So 5/3, that's what? A year and 2/3? Yeah. 1.67 years after the year 2000, because that's time t equals 0. So that is 2001. What month is 2/3 of the way through a year? September. 2/3 of 12 would be 8. Yeah, and you'd be like September 1st. Yeah, right? Is that right? August, September. So that's the next time we're going to hit 4,500, a rabbit population of 4,500, which makes sense because in 2000 we were at 5,000 and decreasing, right? And we hit 4,000 in 2002, 2.5 years later. So somewhere in between there, we should hit 4,500. All right, and then 25/3, that is approximately, say it again, 8 1/3, yeah. 8 1/3, so that's exactly 8 1/3, sorry. Okay, so that is 2008. And 1/3 of the way through the year, April. All right, so now just I'll show you the like super fast and easy way now that we did it the algebraic way. We have a graph of our function. I'm going to graph the line y equals 4,500. And then I just want to know where they cross. Right, so I'm going to intersect f of x with line A, undefined y. No, that's just the slope. I'll try it again. Yeah. F of x. Let's try g of x. Maybe. We'll try it again. Maybe I'm using bad notation. Nope, that's undefined too. What the heck? Sorry, I'm wasting all of your time here. F. Whatever. That's how you do it. I don't know what's wrong with it right now. What am I? Yes. Yeah. I'll figure out what's wrong with it later. I'll tell you when I figure it out. You get the same answers. I was hoping you'd all get to see that. But. Okay, so that's it for the demo portion. You're going to work through some more trig review in your groups. Yeah, sure. So my counting trick is that this is pi over 6 and this is pi over 4, right? Yeah. Okay. And then, so I just like skip all the pi over 4s and count by pi over 6s. So you've got 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. So I'm just skipping the multiples of pi over 4 lines and just labeling the pi over 6 ones. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Yep, you do the same thing with the 4s. So let's see, this guy's pi over 4. I'll do them in orange. So the next one, the quadrantal angle, would be 2 pi over 4. And then the next one's 3 pi over 4. And then 4 pi over 4. And then 5 pi over 4. 6 pi over 4. 7 pi over 4. 8 pi over 4. And if you reduce, then you go through and reduce them all. Yeah. And so you can see like the ones 4 pi over 4 and 6 pi over 6, those both reduce to pi, right? Which was the 180 degrees. 12 pi over 6 and 8 pi over 4, those both reduce to 2 pi.